Boom.
What up?
We here. Are you?
Ooh, apparently you are.
I hope so.
Over there.
Thank you.
You're
Physical
in there.
behavior of matter.
Ooh,
PBoM. Vocab. Special words.
Yep, you guys know the deal with this. Let's get right into it.
You ever seen Good Burger?
I know that word.
I think I know some of these words. No.
I know some of
Yeah.
these words.
Yeah, well, we want you to know all of these words.
Yeah, we're not picking and choosing.
Mm-hmm.
Right into it.
Straight up.
First
Temperature. What's temperature, Mr. Milks?
Temperature specifically is the average kinetic energy. It's the measure of average kinetic energy.
Mm-hmm.
It's a measurement, though.
Mm-hmm.
Like I'm on a ruler.
Yes.
Okay?
Yeah.
Think of it as a heat ruler.
Right. Yeah, it's a heat ruler. Doesn't tell you calories, it tells you degrees.
Mm-hmm.
Now, heat transfer. Heat transfer is pretty simple, straightforward. And what it is all about is about heat traveling from hot things to cold things.
Specifically.
Heat is like the motion of atoms, and it has to move from high concentration to low concentration.
You got to know that it always goes from hot to cold. It never goes from cold to hot. As a matter of fact, in class, you challenge either one of us. We will prove to you that there's no such thing as cold. I can do that.
I think you can. I've never
You
asked
can
you to challenge me.
You can do that.
Moving on.
Moving.
Kinetic energy. Gosh.
Energy of motion.
Right. So this is a great physics picture.
Sure.
That shows roller coasters that everybody's familiar with.
Yep.
The moment when you're at the top of the thing and nobody's moving and just like one scooch
Boom,
forward, you
that
move
motion.
forward. Your potential energy is huge because you're at a high position above the ground.
Okay.
Your kinetic energy is zero. But as soon as you go down that hill, you gain kinetic energy and lose your potential. So your fastest moment is when you're at the very bottom of that.
Notice that
hill.
they're always kind of working
opposite. They really
Right.
are.
So for us, like kinetic energy is going to be like moving fast,
Mm-hmm.
right? And then potential energy is more like stored chemical energy.
Yeah. So kinetic energy is the energy of the motion of atoms and molecules and particles.
Correct.
Potential energy is the energy
Same
stored
picture.
up between bonds, so like in intermolecular forces,
Right.
as well as energy stored up in actual chemical bonds too.
Sure. So for our case, it is more stored energy than it is energy. When we say energy of position, it is more physics.
Right.
But energy of position of molecules now, we're getting
Now we're
along.
talking.
We're getting along
Now
in
we're
those
talking.
lines.
So potential and kinetic energy, we're going to see how they relate to our heating and cooling curves, which kind of look like roller coasters.
A little bit.
Yeah,
With
not
some
one
fans.
that you'd want to go on.
Fans.
Kinetic molecular theory.
There they go. They're doing it. These guys are doing kind of what we would call kinetic molecular theory.
They're obeying the rules. The particles move around. They don't stick to each other. They hit the walls of the container. They transfer energy when they move.
Yes.
And there's a couple other postulates I'm forgetting, but
Mostly empty space.
mostly empty space between the atoms.
So they don't feel their neighbors. But
if you-
it's these 5 postulates.
Right.
So you need to know all 5.
Bing, 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 bing.
And those 5 just set up this condition for how an ideal gas behaves.
So that we can predict gas behavior,
There
which
we
is
go.
again one of our overall objectives.
Again, if I heat a balloon up, is it going to get bigger or smaller?
We know these things already, but we're going to put actual definitions and paper to it. So let's do it. Absolute zero.
Bam!
There
Stopped.
it is. Up 300 Kelvin. Everything's moving.
Stop!
Stopped. 300 Kelvin. Everything moving. Stop. So absolute zero is related to motion.
Yeah, and it's a theoretical thing that we haven't actually got to yet. But under theory, all motion would stop. And we're going to talk to you later about the 3 different kinds of motion.
Right.
1 you really know about, 2 are going to make you think.
Yes. Normal boiling point. There's a whole reference table dedicated to this. Mr. Milk's grabbing the pen. He's highlighting right there. That is the normal boiling point of liquids. So when you put water on the stove, it normally boils at 100 degrees Celsius.
Right. And if you notice, that number 101.3 kilopascals is in the STP.
Standard temperature and pressure. So boiling and vapor pressure are related now. That's what we're going to teach you about.
Yep.
So temperature at which a liquid boils at 1 atmosphere. We only deal with those 4 from this particular chart,
Which
but
is
the
nice.
concept will extend to any liquid.
True.
True.
Curling curve. So notice we are going down, and I'm going to track the phases as my substance goes from gas to liquid to solid, and it's just this graphical representation. And that was one of the things Mr. Monaco was talking about, that picture. We're going to be able to
It's like a
learn.
roller coaster.
Kind of.
Crummy roller coaster either goes all the way up or all the way down.
Yeah, this one's even better, though, to be honest with you.
Maybe
This
more
one's
like a
E1.
water slide.
Yeah.
This is like the stairs walking up to the water slide, and then the other one's like it
Going down, yeah. And this one's funner.
Yeah,
I
I
said it,
love this
funner,
one. I
'cause I
really
like the
love
picture.
the
The particle
animations.
motions going on at the same time. So this one's really good, actually.
It shows you everything. It's heating, the phases of matter, a particle model of the phases of matter, and it shows you the equation
those Q
that
equations
you would use to calculate the amount of heat
Yeah.
at any given point. I love that. I'm going to have
This
to
one
add
is
it to the package.
This one is the greatest one.
Bring it back when we do heating and cooling curve.
Got you. All right, this is a graphical representation of heating the substance, but notice it goes up instead of down.
Yes.
Right.
As you look at the axes, you can figure it out.
Yeah.
Is it being heated or cooled? Well, just pay attention to your units on the axes. Evaporation. Evaporation is what happens at the surface of a liquid.
Yeah.
It wants to become a gas, so only the molecules at the surface are able to become a gas. So when this GIF starts over again, it will show all of the liquid, and then it bursts off into the vapor phase.
Yeah. And I always think of evaporation can happen maybe without so much heat, where boiling needs the heat to kind of get it up to that space.
Evaporation heats with ice. Evaporation happens with ice in your freezer. If you ever put an ice cube in the freezer and came back a couple months later, it's like half the size. You're like, wait a minute, where'd it go? Well, it evaporated. It was freezing cold. How could that happen?
Yeah, it happens. Pressure.
Pressure. All right.
All right. When the surface changes into the gas phase, notice it doesn't change from the bottom either. That conceptually is important. It does change from the top.
Yeah.
Okay. Heat of fusion.
Heat of fusion is a quantity that is used when we calculate a change in phase. Fusion specifically for the freezing and melting. So there's no change in temperature when an ice cube freezes or it melts from 0 degrees to 0 degrees. It just changes phase. So you have to have a special equation, including heat of fusion, in there in order to calculate how much heat was involved in that phase change.
Yeah. Special note, this fusion does mean melting.
Yes.
So you might want to put a note there because it don't sound like melting. It sounds
And
like
freezing.
fusing together.
Yeah, it means both, really.
It does, but it's it's usually always associated with the melting, which doesn't seem to make sense.
Yeah, it is.
And
what
the
it is.
vaporization is just at the top here now,
Right.
the top flat, and that's going to be specifically now going from liquid to vapor.
Yeah.
Right. And so again, very much the same definition, except for now I'm going to a gas. Completely evaporate a gas with no change in temperature.
Got you. Heat of reaction. We're going to show you heats of reaction on table I, just because this unit is about heat.
Yes.
Temperature is kind of where it fits, even though we're not going to do these chemical reactions. We're going to see how a potential energy diagram is created, similar to a heating or cooling curve, that tracks the changes in heat for a reaction. And delta H
is in between the reactants and the products. You can see it labeled there.
It's the overall amount of heat absorbed or released in a chemical reaction.
Correct. So there it is. It's always products minus reactants, shows the overall change.
And we ignore the amount of heat it takes to initiate the reaction usually. So
all right, here we go. Check it.
Melting point.
Melting point.
There
when
it is.
I go from solid to liquid. And guess what?
Freezing point's the same thing.
Freezing point's the same thing, just opposite direction, going from liquid to solid. So you need to know that it's both. Could be either way, depending if it's a heating curve or a cooling curve.
Yeah, it depends on which direction heat's flowing. If heat's flowing into the object of interest, it's going to be melting. If it's flowing away, it's going to be freezing.
Vapor pressure is specifically the pressure of the liquid pushing up, right? Forming that vapor out of the liquid.
Right. So certain liquids have different vapor pressures.
Yes, depending on their intermolecular
It's like a
forces.
push-pull between the atmosphere pushing down and the liquid's vapor pressure pushing back. Whichever one's stronger is going to win.
Right.
That's why some things boil at low temperature.
Calories is another word for heat, and so a calorimeter is something we use for it. This is a model of a bomb calorimeter.
There it is.
And
Measuring
it measures heat.
Boiling point, condensation point.
You got that too, boiling?
Yep, that is the temperature at which a substance changes phase from gas to liquid, liquid to gas.
Ideal gas behavior.
There's a picture.
There's a picture. We got gases in a box, in a closed container. High temperature, low pressure. They will obey KMT the most.
Right. So memorize that ideal gas behavior is when it's under high pressure, high temperature, low pressure.
High temperature, low pressure.
There's our combined gas law equation.
This is in the table T.
It's a plug and chug. Once you
It's a
understand
plug and
it,
chug.
it's really not scary.
Looks scary, but it's not.
It combines 3 or 4 laws.
Yeah, these 3
into
laws.
that one.
Yep. And guess what? You don't have to memorize those 3 single laws. We're going to teach you about them, but you don't need to know that.
Because they only make sense if we're going to teach you the combined law to teach
Right.
each one along the way.
And we've talked about this STP a lot. Here it is from your table, right? This is what the constants are.
Yep.
There you go. Standard temperature and pressure, 0 degrees Celsius, 1 atmosphere, set of
Set of conditions to compare.
And we out.
Do your vocab quiz for my kids on the homework classroom.
Mine will be available in class. See you.
See ya.